Hello again. Once again, this is Shank Valagati, engine programmer, and I would like to demonstrate one of my favorite little projects here. The something that I would like to call a Jello Cube. When you can see the structure, it is a 4 by 4 cube of red spheres that I actually have rendered in OpenGL. And the unique thing about this structure that it is not static; it is actually dynamic as we speak, between each point on this cube and the 26 adjacent vertices on that cube are spring mass damper systems. Yes, each sphere is connected to the sphere next to it with a spring and a damper, and each sphere has a mass of its own. To all the spheres and connected to all the spheres um, adjacent directly, adjacent at an angle, and adjacent at an angle with depth. So what happens is that we have a stable, cohesive structure, an amorphous solid, a deformable solid, that is able to maintain its shape. So what I'm going to do here is add a little impulse by resetting the cube to a higher height with a little bit of torque, and spin and watch it land. And as you can see here, the Jello Cube lands, deforms, and eventually stabilizes to maintain its integral shape. You can see really how materials are made on a molecular level, like Jello, for example, that where the springs and the masses and of the molecules, and springs that attach the molecules together, really work to keep the molecules together, but far enough apart that they actually maintain a solid extruding surface. I'm particularly proud of this project because, I mean, it really does look like a Jello cube, and the particle systems that I am using here, I mean, are pretty simple. I'm just rendering spheres at the correct point and then integrating them forward in time. The integrative method that I use is actually Verlet integration. I can try Runge-Kutta, which seemed a little bit too complicated for this, and Euler, which actually did not work out too well due to floating point errors that abound in the floating point errors that abound in the forward Euler integration. Simply because as any oscillation occurs with floating point errors with forward Euler, the velocity is taken to be a little bit bigger than the last oscillation, and it gets a little bit bigger each time. And so what happens is that the cube actually oscillates so much that it explodes and loses all integrity. But Verlet is a great integrative method, especially for particle systems, because it takes acceleration and past position into account rather than velocity. So you really have less of those situations where things get out of hand. I'll go ahead and demonstrate this once again. You can really see how everything bounces and the cube kind of gets into a mess, but all the springs there push it back together, and eventually it becomes a cohesive cube again.